Thank you for inviting me. This work is done. This is work done together with Jakob, Andre, and Daniel. Recent work, and also it will tap into old works done by the late Jukiewicz and by Renate Lund and Andre and myself. I will start with some textbook stuff, simply because I think it's important to get the way that we are thinking about this clear. So I will start with a 5 to the 4th theory in 4th dimension, a lattice 5 to the 4th theory, and discuss how would one check whether there is an ultraviolet fixed point on this in this lattice theory. So what I say here is, as I said, just textbook stuff, and you can find everything in much more detail in the very nice book of Montved and Münster called the Field Theory on the Lattice. So we start out by a 5 to the 4th theory, the simplest discretization. We have a kinetic term, we have a mass term, and a 5 to the 4th term. And the lattice spacing is put to 1, and all fields and coupling constants are dimensionless. So we have to make some definition of every normalized coupling constant in terms of the bare coupling constant of the theory. And one standard definition on the lattice is to say that take the one particle irreducible 4-point function at 0 momentum and these bare coupling constants. You can now express this in terms of bare quantities on the lattice, which you can directly measure. So then the expression is given here, where this susceptibility, this is just this is a Fourier transform at 0 momentum, so it is what corresponds to this, but it is the connected function, not the one particle irreducible function. And then you divide by the 2-point function here, the second derivative of the momentum. This is what this is. That is squared. So you see that this normalized coupling constant can be expressed in terms of bare quantities on the lattice very explicitly, but of course usually it's a little bit of a complicated expression. So here's the phase diagram of the theory. For positive mass squared, you have a unbroken phase, and for negative mass squared, you have a broken phase. And there's a second-order phase transition, which is separating the two. And at this phase transition line, the correlation length is infinite. So the correlation length, how is it defined? This is defined by the exponential decay of the 2-point function on the lattice. So here's the definition. So in the discussion from now on, it is convenient actually to change variables from the bare mass to the correlation lengths. And here's the way to do it. So in principle, locally, you can clearly do it. We just assume that you can do it without any problem also kind of globally. And then the second order phase transition line is the correlation length is equal to infinity. And I have then kind of redrawn the phase diagram here. Psi, the correlation length is equal to infinity. This is just this line here. And on this line, there can be infrared fixed points, ultraviolet fixed points, another infrared fixed point, etc. A priori, we don't know what is the situation, but this is what we want to find out. And we want to find out in particular whether there is an ultraviolet fixed point for this 5 to the 4th theory. So for any choice of the bare coupling constant and the correlation lengths, or the bare mass, depending on what you like, then you can calculate the renormalized coupling constant. This was what I just showed to you. So let's take this point here. We calculate the renormalized coupling constant, and then we follow a line here at which this renormalized coupling constant stays fixed. So this will be a curve in this 2-dimensional coupling constant space. And how does this curve go? It can go like this. So it can never reach the region where the correlation length is infinite, or it could reach the critical surface. If it reaches the critical surface, then we have a UV fixed point. So in principle, it's quite easy to check. Assume that you could follow this line either by analytical calculations or numerical simulations, and all curves, no matter what choice you take here, it should converge to the same point. So the fact that the renormalized coupling constant is fixed when you change the correlation lengths, it can be expressed by an equation like this. So this curve here is characterized by the bare coupling constant being a function of the correlation lengths. And when you differentiate, when you do the partial differentiation and introduce the beta functions of the bare coupling constant and the renormalized coupling constant. So in the first case, you keep the renormalized coupling constant fixed, and in the other, the bare coupling constant fixed. Then kind of this equation here, leading to this curve here, it gives a relation between the two beta functions. So they're not identical, but at critical points, you can show that their functional form is the same, basically, but not necessarily outside this. So it is basically the situation, and it is kind of what we want to use also in our lattice gravity theory to identify the ultraviolet fixed point. So there are, as we see, there are two beta functions here. In one case, we keep the renormalized coupling constant fixed. In the other case, we keep the bare coupling constant fixed. So what happens if you now look at this diagram here? What happens if we keep the bare coupling constant fixed? Then we approach infinite correlation lengths in this way here. So we approach the critical surface like this, and you see that we are crossing various values of the renormalized coupling constants. So what it tells us is that when we keep this bare coupling constant fixed and approach the critical surface, then the renormalized coupling constant will flow towards its infrared value. On the other hand, if we can reverse this, as I already have said, if we keep the renormalized coupling constant fixed, no matter where we start, and we follow the curve of constant, then the bare coupling constant will flow to the ultraviolet fixed point. So this is reflected in the different sign which is used here for these two. So we have these two limits, and that's basically what I want you to take away from this figure here. So here I've just shown some lot of how the beta function in terms of the bare quantities would look like if there was a ultraviolet fixed point for 5 to the 4th theory. So it would start out in the infrared, and we know it here. We can calculate perturbatively in the 5 to the 4th theory, but then it would turn and it would cross this line here. So here you can, and the renormalized one would have a similar shape, as I just said. I mean, the kind of renormalized beta function as function of the renormalized coupling constant. So here we can just approximate it by its linear form, and then we can integrate it, and then what we get is that chi naught as a function of the correlation length is given by the ultraviolet value of the fixed point, and then some power correction. And you see that if the derivative here in the UV fixed point is negative, then the correlation length goes to infinity when the bare coupling goes to the ultraviolet fixed point. And so this is what I want you to take away from here, that we have this kind of relation here. The way that the bare coupling constant will approach the kind of UV fixed point. So until now, we have just assumed that the lattice length is fixed, A, let this be the length of a length, B1. But we can, if we want now, we can trade the correlation lengths going to infinity by a change of the cutoff, A going to 0, by introducing a kind of renormalized mass. So the way we do it is we just say, okay, we have the lattice space, and then this becomes a real physical space distance if you multiply it with A, and similar the correlation length. If you multiply the lattice correlation with A, it becomes a physical correlation length in 1 over the inverse kind of renormalized mass. And we can now take a limit where this correlation length is kept fixed. The lattice correlation is equal to infinity, that is, we approach the critical surface, and we take A to 0. And if you do it in this organized way here, you can of course choose other ways to do it, but if you do it like this, then you see that the exponential fall off of the lattice function survives in the continuum limit. And so this implies that we can find a continuum kind of renormalized 2-point function, which falls off exponentially, exactly when the lattice spacing goes to 0. Now, if we in addition can follow a path, as I described before, such that the renormalized coupling constant stays fixed when we change the bare coupling constant and the correlation length going to infinity, if this can stay fixed all the way to the UV fixed point, then in addition, we have an interacting continuum quantum field theory with these two renormalized coupling constants, MR and KR. So it is a way that you would find this interacting continuum quantum field theory in case of phi to the fourth theory. And well, I should say that the kind of seminal work of Martin Lüscher and Peter Weiss, they used exactly this figure to prove, or at least give very strong arguments, that there is no UV fixed point for phi to the fourth theory. Because when they did the calculations, they always found a curve like this. They could never, no matter where they started out in this coupling constant, bare coupling constant space, they could get to the critical surface. And they took this as evidence that there is no UV fixed point. So until now, in this discussion, I have assumed that the lattice size is actually infinite. Well, since we are discussing correlation lengths going to infinity. But in actual Monte Carlo lattice simulations, of course, the number of lattice points is finite. And the lattice has a certain size, L to the fourth equal to N4, the number of lattice points. And clearly the correlation length has to be less than L. So for a given renormalized coupling constant, we can fine-tune the bare coupling constant such that the correlation length assumes its maximal value. And then if we insert in the equation I showed you before, then we have this equation here. So for different kind of renormalized coupling constants, then we have these different curves here. They all have the same power law dependence here when we approach this point, but the constant in front is kind of different, and this is why you get this family of curves. And then putting in that chi maximum is equal to L, then this becomes an equation in terms of L. And again, when the derivative here is negative, you see that when L goes to infinity, this goes to the UV fixed point. And basically, this relation is the foundation of finite size scaling. And this coupling constant here, this is called the pseudo-critical coupling. Since we cannot really, for a given L, we cannot approach in an organized way this real coupling constant here. Well, since we cannot increase chi psi larger than L. But if we study the lattice system for different L, then we can determine this exponent. And it's exactly what we will do. And so you can say that this is basically a critical exponent for the lattice theory, I mean, the most important one. So this was just a very short review of how you would find this UV fixed point for phi to the fourth theory, or not find it. So we will see what happens when we come to lattice quantum gravity, or other what is called dynamical triangulations or causal dynamical triangulations. So I don't have any time to go into any discussion of this. I will just give you a little feeling of what goes into this. So the classical action is written here. This is the Einstein-Hilbert action. And now it is, of course, very easy to define a quantum field theory. I mean, you just write down this this formula here, this is a partition function for quantum gravity. Of course, the problems they are in the detail of how to make sense of this, as you all know. So what is precisely meant by the measure, for instance? So in this case of our Lorentzian, so in CDT, so let me talk about CDT here. So in CDT, I mean, we start out by assuming we have a Lorentzian spacetime, and inspired by canonical quantization, we assume that we have a time, we can take it as proper time, we have a time foliation, and now such a spacetime we triangulate by using building blocks. And by using building blocks, it means that we glue together these building blocks to what becomes a piecewise linear manifold. And we know the edge lengths of these building blocks, and then we can use Radie action for piecewise linear manifolds to calculate the actual action in the path integral. So it's a somewhat remarkable aspect that gluing it together, I mean, the way that we are doing it, which I will tell you in a split second here, one can actually rotate each such Lorentzian geometry to an Euclidean geometry, where each building block is now just a 4 simplex where all links have the same length A. So this length then plays the role of a UV cutoff, precisely as in ordinary lattice gauge series. So here is the way that we build up these time foliated geometries. Now I go directly to Euclidean here to describe it. So we have a time slicing. Time is discretized here in units of 1, and similar space is kind of discretized in units of 1. So each time slice has a fixed geometry. Here it's written as R3, but in the computer simulation we're using S3, a compact space. So we triangulate this compact space by gluing together these tetrahedra here, so that they have the topology of S3, and similar up here. So we have then 2 3-dimensional triangulations. And now we have to fill out the slab, the 4-dimensional slab between these 2 3-dimensional surfaces, and we do it in the following way. For the tetrahedra here, we connect it to a point up here. If there is a triangle here, we connect it to a link up here. If there's a link here, we connect it to a triangle, and a vertex here, we connect it to a tetrahedron, up here. And then we glue together all these 4-dimensional simplices that we create in this way, in such a way, in all possible ways, but in such a way that cutting it in the middle, I mean, the topology is preserved to be here R3, but S3 in our case. And then the path integral consists of summing over all possible 3-dimensional triangulations that we make here and all 4-dimensional that we get in this way. So it is how the and then for each triangulation, then we use the Radie action as a weight. And now the remarkable feature also is that the Radie action becomes very simple when we use identical building blocks. So for a given 4-dimensional triangulation, let N4 be the number of 4 simplices, N2 the number of triangles, and N0 the number of vertices. And then the Euclidean Radie action for this could either be dynamical triangulations or CDT is simply given by some constant times N2 plus another constant times N4. And by using what is called the Somerville relations, one can express N2 in terms of a linear combination of N4 and N0. So one can write it either like this or like this. And in the case of CDT, then we take the liberty, well, in the Wilsonian spirit, to assign different coupling constants to N32 and N41, where the 4 simplices, which we call 3-2 or 2-3, they are the ones which connects triangles to links, and the one we call 4-1 or 1-4 is the one which connects tetrahedra to vertices. But as we will see, this doesn't really play any role, which is nice, but well, it plays some role, but not any important role in the region of interest for us. So So then our red axis becomes really simple. It just depends on these global quantities. And historically, I mean, we didn't use these coupling constants, but we introduced a delta and a K4, which is linear combinations of these guys, such that the action could be written like this. And this delta, if it's put to 0, then we just get this action up here. And if it's different from 0, it will give a relative weight to the case 2,3 relative to K4,1. And and K4 here, this constant just monitor the number of 4 simplicities. So now the whole story is the following. We have our formal continuum partition function. We describe it as a lattice partition function of CDT, a kind of Lorentzian with these 3 coupling constants, which I just showed to you. Then we rotate each configuration to Euclidean space, keep the same coupling constants. And then this partition function is now given by this explicit sum here over the kind of triangulations I just described. And since N4 appear here and only here, then we can take it outside and sum over N4, and then this is the sum of all the triangulations of the kind we just discussed, but with a fixed N4. Now, this set of triangulations here, they grow exponentially in N4 with some constant, which depends on the bare coupling constant we put in, but it has this form here. So you see that we can combine this with this thing here, so you get e to the minus K4 critical times N4 up here in the exponent. And this function f here is sub-leading compared to this exponential growth. So this partition function is well defined when K4 is larger than K4 critical here. And it is ill-defined. It's just plain divergent when K4 is less than K4. So kind of clearly, we are interested in large N4s. So we have to study the region where K4 goes to K4 critical. However, from a numerical point of view, it is much more convenient to study a system with fixed N4. And thus K4 will not play the role of a coupling constant in the simulations, not directly, but we compensate for that by studying the systems for various N4s. And then one can make the connection between these situations. So one can say that effectively what we are doing in the Monte Carlo simulations, then we are studying the sub-leading part here of this thing here. But is known from 2D quantum gravity with causal dynamical triangulations or DT, that all the continuum physics is in this sub-leading part here. More or less. I should say all kind of non-trivial physics is in this sub-leading part. So this is perfectly fine. So it is a setup. So here I've drawn, we had 3 coupling constants, but delta K0 and N4 to the minus first I plotted here. So I plotted this instead of K4 because it is the quantity that we can vary, and we are of course interested in N4 being large, even N4 being infinite. So this is this plane here. This is the plane of N4 being infinite. And of course, we only have a real phase diagram when N4 is infinite, because you have to have infinite number of I mean, the lattice has to be of infinite size to have real critical behavior. So here's a phase diagram. I will not go into any discussion of this, only say that this phase here, called the de Sitter phase, is the one which has our interest. So we don't think the other phases really corresponds to any continuum physics, but well, maybe phase CB can be of some interest, but the de Sitter space is what has our interest. So precisely what do we see? Well, so up here, we have plotted N3. So N3, let me go back and remind you how to set up is N3 to a certain time is the number of this is the free volume in a lattice free volume. This is simply the number of tetrahedra in at this time slice. So for each time slice, this is easy to measure in the simulations. Is more or less given to us, and this histogram is a snapshot of a configuration. So the time is chosen here to be 80, and the number of pore simplices is 362,000, and you see a histogram like this. So now you take the average of a couple of million of these configurations, and then you get this beautiful smooth red curve here. And what you see is that there is what we call a blob here in the middle. Well, they are centered in some way, which I have no time to discuss how to do. And then there's a stalk out here, and the stalk, I mean, so the spatial volume of the time slices up here, they're basically of cut-off size. I mean, so we don't allow the computer program to for the spatial volume to go to 0, but they really like to be almost the minimal value, which is 5. If you want to glue together a number of four-dimensional simplices to form S4, then you have to glue together at least 5 of them if you want a kind of regular geometry. So it's only the blob here that we're interested in. And this blob, so you see, it doesn't really extend all the way out here. And in fact, the size, the width of this blob, it scales like N4 to 1/4. And similar, the height here, it scales, as you can see here, as N4 to 3/4. And this is exactly what you would expect if you had a four-dimensional nice geometry. Then the linear dimension would be N4 to 1/4. So this is what we see. And not only do we see that, we see that they fit perfectly well with this explicit function cosine cube. So the only thing here which depends on the choice of bare coupling constants in this de Sitter space is the omega. So it will depend on that, but apart from that, there's no dependence. So now when we take these millions of superpositions to get this curve, we can also measure the fluctuations of the free volume. And this is shown on the curve here. And it also follows a kind of universal behavior. Again, with this in the time with 1/n4 setting the scale, and a new coupling constant gamma enters here. Basically, I mean, the value when I is equal to 0. So 0 is just putting in the center here. So now we can introduce scaling variables. I mean, basically, you can call them dimensionless variable. Everything is dimensionless, but in terms of dimension of space. So this is time scaling, this is space scaled with this, and this is just the time steps in the scale variable. And then all curves, I mean, well, assuming that N4 is sufficiently large, this is only true for large N4s, this form, they collapse to one curve. And similar, the fluctuations, they collapse to one curve, but multiplied by this factor here. So the fluctuations go to 0 when N4 goes to infinity. But the fact that we observe this finite size scaling, we take this as a sign that we have a correlation length which is equal to the linear dimension of the system for arbitrary values of these in the interior of this phase. So I will discuss the nature of this correlation length at the end of the talk. I think it is very interesting, but it is our basic assumption, and the way that we want to connect to the 5⁴ theory, where I expressed everything in terms of this correlation length. So this is how we go. So I should say here that both the measurements of the expectation value of the free volume and the fluctuations are perfectly described up to the numerical accuracy that we can measure is by this effective action that I've written down here. So here's a kinetic term, and here's another term, and these are the two coupling constants which enters because this delta is related to the omega that we observed. I mean the width in the time direction of the blob. They're related like this. Delta is omega to 3/8 times some constant, and these constants I'll come back to in a second. But now when I put in the final, I mean these dimensionless variables, then the effective action simply becomes something like this. And of course, if you solve the classical equation for this action in reduced variables, you get exactly this. This is the solution to this equation under the constraint that the integral of n3 here is equal to 1. And this is just kind of telling us that the sum of n3s are basically summing up to the total volume n4. And these two, so what we can make, on the lattice, we have to measure these two coupling constants, and they depend, of course, on the bare coupling constants and on n4. But as I already have said, for n4 large, they just go to constant values. So these observations are old. They are 15 years old, or at least 10 years old. And what we said in the old days, like 10 years ago, then we wanted to relate this to ultraviolet fixed point. And then what we said at that time was, now, let us be very naive. Well, this is the only thing I master to be, that is naive. So let's be very naive and say V4 is proportional to N4 times A to the fourth, and similar with V3. And now let's keep this V4 fixed. Then we clearly, if that is possible, then clearly we have a limit where N4 has to go to infinity and A has to go to 0. But this is exactly what we want. So this seems to be good, and this seems to be very similar in spirit to what I just told you for the 5 to the 4th theory. We have this zero normalized mass, or the this corresponding correlation length, and we write it like A times the lattice correlation length. And then we keep this fixed, and we take A to 0 and this to infinity. And when I write this in the same way, I write the fourth root of this to be A times n to the fourth, and I just declared that we view this as a correlation length. So you see that it becomes exactly the same. We keep this fixed, we take A to 0, the correlation length goes to infinity. And so if V3 is finite, also the fluctuations should be finite in the continuum. So we view these as kind of renormalized continuum quantities, and I just show you this curve again. I mean, if the red curve is a continuum curve, really showing our continuum universe, then of course the fluctuations better also be finite. At least everything else would be drastic. So this means that this should be a constant when we take A to 0. And now I express it in terms of n3s, and these n3s, this was the fluctuations, and these were the measures. I put these functions in, and you see I have this formula here. So this is clearly finite when n4 goes to infinity. But clearly this cannot be true if the bare coupling constants are constant. So the only way to get this satisfied, this is to find such a limit, to change these bare coupling constants and find a path as a function of n4 such that this is satisfied. So it was where we were 10 years ago, and we tried to do that, and we have even written an article about it. And so omega squared times gamma has to be proportional to n4. We have to find such a path in the bare coupling constant space. And we couldn't find it. But now we can, because we have much better data. So now we can find it. So what we saw in the old days, it was that this quantity, it changed a little bit, but not very dramatically. And it changed only when we moved towards the AC transition. It changed in the right direction. So let me show you the phase diagram again. So here's the AC transition. And we didn't, so only when we moved like this, only when we moved like this, it changed in the right way. But we didn't like that because seemingly this transition, it was a first order transition. And you cannot use ordinary first order transitions to define a continuum limit because the correlation length in first order transitions is finite. So it was a sad state of affair 10 years ago, but now the situation has improved. And this relation here, I will now kind of rewrite this by comparing to the functional normalization group. So now I will mistreat the functional normalization group in a grand way. I hope experts will not be too upset, but I had to do that in order to compare with our lattice simulations. So first of all, I take the simplest truncation used for the functional normalization group. This is the one here where we have a running coupling constant G and a running coupling constant lambda. As you all know, the seminal work of Martin Reuter, when he used this and he calculated these running coupling constants, what he saw was that there was an ultraviolet fixed point. So in terms of dimensionless coupling constants, little g and little lambda, they go to fixed value. And well, in particular, if you take the kind of dimensionless product of these two, of course, they will also go then to some constant value. So now here's where I will mistreat this in a grand way. So I will simply say, this is my effective action where quantum effect is entirely absorbed in these running coupling constants. And now my ground state will be simply be the extremum of this with respect to G. And even more, so this is written for Euclidean metric. And of course, I mean, the solution is just Euclidean de Sitter space. And the radius then will depend on the coupling constant lambda. It will not depend on G, but it will depend on lambda, simply by solving this classical equation of motion. The fluctuations will depend on G, but not the radius. But one can, of course, study fluctuations around this solution. And let us now just do it in the very simplest possible way, where we use a mini superspace version of this in order to compare with lattice results. So I simply take a proper time choice of matrix written like this, where this is the scale factor of the universe, and the V3 volume is then 2 pi squared R cubed. And when I put this variable in the Einstein-Hilbert action, I get this action here. And I now fix the integral of V3 to be V4, where V4 is the volume of the corresponding force sphere here, corresponding to this lambda. And now, if I introduce dimensionless variables, then you see that I get a functional form which is identical to the one that we have, that we derived on the lattice. On the lattice, we derived it by integrating out all degrees of freedom, except the scale factor. I mean, so we didn't make any approximation. Here, of course, there's approximations going into this of various kind. So we have, this thing here was what was the square root of N4 divided by gamma. And then we had a delta here, not this delta naught. So these delta naughts, they were defined here. Omega naught was this, and delta naught was this thing here. And they just come from the force sphere. They just come from having a force sphere of volume 1. Because this is the solution, of course. When we solve the classical equation, we get exactly, I mean, the standard force sphere, where S is now the force sphere of radius 1, of volume 1, where S is the proper time measured from equator of this force. So it doesn't make sense to make such perturbative expansion around here. Well, the effective coupling constant is clearly given by this, which can be written in this way, which can be written in this way again, where these were the dimensionless. So in the function in the functional normalization group analysis, this eta, I call it now, the product of these two is of course running from the present day's values, which is 10 to the minus 120, to the value at the fixed point. Of course, this value is not really universal, but for a number of different regularizations, one always finds that this product is less than 0.12. So it never grows large. So actually, it seems that simple first-order Gaussian perturbation theory around this solution is not too bad an approximation all the way to the ultraviolet fixed point. But of course, this beta function, as function of eta, has been calculated in functional normalization group. So it was first done by, I think, Kevin Falls in 21, where he argued that in a certain, what is called essential renormalization, one can view this as the only kind of relevant coupling constant. And also there's a later work of Kawai and Ota, slightly different in spirit, but still more or less the same, where they also calculate the beta function for this. And you find a curve like this. So very similar to the 5 to the 4th, the putative 5 to the 4th theory. We have an ultraviolet fixed point. And the range of renormalized coupling constants here, they lie in this range here. So, but we can choose it to be fixed. So can now let us ignore, for simplicity, the fact that delta is different from delta naught, and also let us ignore this coupling constant capital delta. So we only have k naught and we have n4 here, and then from the two effective coupling constants, the same functional form, then we identify these two ratios. So here we have the bare lattice quantities. Here we have what we view as the renormalized coupling constants of GR. So it should be compared to this 5 to the 4th theory. Here we had the renormalized coupling constant defined in some way. I'm not really specifying exactly how it's defined here in terms of the lattice, but we assume that, morally speaking, one can kind of rely on this kind of relation. And then this is expressed as a complicated function of the bare coupling constants in the same way as this gamma is a complicated function of k naught and n4. So n4 again is to be viewed as psi here. So if you had used finite size scaling here, we could have used n4 to 1/4 here also. So we now have the same options as for the 5 to the 4th lattice theory. We can keep the bare coupling constant k naught here. We can keep that fixed and take n4 to infinity. That's the correlation links to infinity. And then the renormalized coupling constant should flow to the infrared fixed point. On the other hand, if we keep the renormalized coupling constant fixed and take n4 to infinity, then k naught should flow to the ultraviolet fixed point, provided it exists. So this is what we're going to study. So I've shown this figure again here. So now we keep the coupling constant, the bare coupling constant fixed. And since gamma will be independent of n4, being sufficiently large, then it is seen from kind of this relation here that if this is independent of n4, then the renormalized coupling constant, the product of these goes to 0. So this means that we flow to the infrared fixed point here in terms of kind of renormalized quantities. So any point here in the interior of the CD phase should then be identified with a critical surface because the correlation length is infinite here, and it should correspond to the Gaussian fixed point. So that is how we flow to the Gaussian fixed point in the lattice theory. So if you now look at this relation here, well, psi is equal to n4, and if we plug in that we also expect that the 4 volume, these two should be identified up to some constant of proportionality, then you can see that if you plug this n4 to the 4th in here, then n4 drops out, and you see that you get a squared equal to this. So at the Gaussian fixed point, this g of k, it just floats to our Newton constant as we know it today. We can think about it like that. Simply the Planck length for small k. So the lattice spacing, it doesn't go to 0. It stops at the Planck length, well, divided by this thing. But this is just a constant. But this is an infrared fixed point. So in principle, this is perfectly fine. I mean, if you think about it in a Wilsonian sense, I mean, at the infrared fixed point, I mean, the correlation length goes to infinity. Wilson was always thinking about a lattice where he didn't change the lattice spacing as such when he wanted to go to an infrared fixed point and so on. So this is absolutely fine. So the correlation length, now plugging this in again, it now goes as 1 over k squared. We can also write it like this if we introduce this formula here. So indeed, when k goes to 0 in the functional normalization group, our correlation, lattice correlation length, it will go to infinity, as it should go, because we are approaching the critical surface. And actually, if you write it down, I mean, at the Gaussian fixed point, then this eta, it scales like k to the 4th. I mean, this is a functional normalization group just at the Gaussian fixed point. It looks like this. And we have, of course, the same equation here on the lattice because of this relation between the two. So everything is kind of understandable at the Gaussian fixed point. But of course, we are more interested in the ultraviolet fixed point. So let us discuss the ultraviolet limit. So there, again, appealing to the phi to the 4th theory, let's fix the renormalized coupling constant. I will ignore delta again for notational simplicity. And then we have to have a relation like this. So the question is, can we find a path k naught in the bare coupling constant plane to the putative fixed point in such a way that this is satisfied? So, so first we have to, but until now I've assumed that this delta which appeared in our effective action was the same as the one which appears in Einstein-Hilbert gravity, and it is not. So can we compensate for this in an easy way? Yes, we can, because if we can rescale the lattice spacing in the time direction such that the size of the lattice, nt, the number of steps in this block, times at is equal to the spatial size, then we have a round sphere. And in principle, we are allowed to do such a rescaling because anyway, from the very beginning in our construction, we broke the invariance between space and time explicitly by introducing this time fluctuation. So we are allowed to do a finite rescaling to obtain what we could call a maximal isotropy between space and time, namely around S4. So this is just what we are doing, very simple. And then we end up with this relation. So you see that this is, except that now there are some explicit constants here referring to the functional normalization group, then you see that this is exactly the kind of relation that we studied already 10 years ago, and which we were not so happy with, but that's because of the inferior kind of numerical data. So first of all, it's clear that the left-hand side has to go to infinity, and this only happens at the AC transition line. So now we want to study the situation when we approach this AC transition line. And here we will use what I said about finite size scaling. So for any given N4, there is a pseudo-critical critical point, the closest that we can get to the real critical point at in infinite volume at the AC transition. And at this pseudocritical point, in principle, we can measure omega and we can measure gamma. And at the critical surface, when N4 is equal to infinity, then for any interior point in the de Sitter space, then this gamma k is finite and omega k is finite. But when we go to the border of the asymptotic line, then we know that this diverges, or this is what we measure. And then we assume that it diverges when N4 is infinity. We assume it diverges like this. And what we see is that omega goes to 0, actually. So we assume it goes to 0, kind of like this, with two exponents, alpha and beta. And we can now measure these using finite size scaling, because the pseudo-critical point should approach the critical point in a certain way with some critical exponent. And this is related to the beta function, the kind of derivative of the beta function, as we discussed in the ultraviolet fixed point. And then when we plug this thing in here, the difference here will just be a function of n. Then we see that this gamma should scale to infinity like this, and this omega should go to 0 like this as a function of N4. And in particular, the product of these two, it should scale like this, with these two exponents, alpha minus 2 beta. But kind of recall that actually, so we wanted this product to scale as the square root of N4. So clearly that is impossible if this whole coefficient here is kind of less than 1/2. If it's larger than 1/2, then no problem, because then we have this curve here, and we can choose, I mean, the real curve where the product here is constant to be on this side here. But for a given N4, we can never kind of go beyond this thing here, because this is the maximum kind of value that we can obtain for these coupling. So this is basically the requirement for having an ultraviolet fixed point. So what do we see? What do we measure?
Sorry, Jan. Just to let you know, so you're going since 55 minutes. So if you could wrap up in the next 5 to 10 minutes, that would be
good. Yeah.
So we have time for questions.
Don't worry. So what do we see? Well, here is gamma times omega squared plotted. This is N4 in the blob outside here, and this is this value here. And this is a double logarithmic plot. So, well, I should say all data in double logarithmic plots can be fitted by straight lines. So this is what we have done here. But this is, of course, what would come out here. If you take the log on both sides, then we should get a straight line. So what do we see? So here's kind of the result. This coefficient should be larger than 1/2. Is it larger than 1/2? Yes. Great. We have seen ultraviolet fixed point. But unfortunately, you see the error bars, and you should take the error bars seriously. This is real experiments, and it's absolutely non-trivial. I have no time to go into discuss how we extract this, but this is not trivial. We have the hysteresis and all kind of things associated with this phase transition. It is non-trivial to extract this. So there are real error bars here. And so, unfortunately, we cannot say with too convincingly that we have seen this point. But it is not ruled out. In fact, I mean, I've been really agonizing about this value. Had it been 0.6, then you could say, great. Then still the error bars should be smaller in order to say this convincingly, but that could be done by numerical simulations. We just use 5 times more data. Had it been 0.4, then we could say the ultraviolet fixed point was ruled out. But 0.5, I mean, assuming that this value is really correct, 0.54, then it's almost impossible in a finite time to increase the error bars simply by simulations in such a way that you can say that with 5 sigmas kind of accuracy. So that is the situation now. So I would say that it's an exciting situation in some sense, but well, I hope that I convince you that in a certain way there's a straightforward procedure to test this on a lattice. Unfortunately, our test is just for some magic reason, which maybe can be understood. I'm not still quite sure about this. This exponent is just at the borderline of what it should be. It could be good or it could be bad. But this is the situation. So I will just use a few minutes here to talk about the correlation links, because I think this is quite important for lattice gravity. So the whole analysis here, it has been based on the observation that we have finite size scaling, and that this scaling implies that we have a correlation length psi equal to n4 to 1/4. Of course, on ordinary lattices, such an identification of correlation lengths and finite size scaling is unproblematic, because you start out with n4 equal to infinity, and the correlation lengths defined by the correlation lengths of fields living on the lattice are completely independent of this n4, if it's only large enough, of course. So one first introduces the correlation lengths, and then one diminish the lattice such that it becomes equal to the correlation lengths, and then you have finite size scaling. But here we have no such separation between n4 and psi. But even more puzzling, you can ask, what is correlated with this correlation length? And the answer here is space-time points. And I think this is an important point which should be emphasized somehow. So a correlation between space-time points is of course trivial for a fixed space-time. But it simply becomes the simplest diffeomorphism invariant correlation function in quantum gravity, which directly probes both the short distance and long distance fractal structure of spacetime. And also, it is not really related to the propagation of ordinary degrees of freedom, like spin 2 particles or something like that. So there's no need for ordinary second order phase transition in order to study this. Let's see. Yeah, okay. So here I define such a correlation function in the continuum. So how would you define such a correlation function of space-time points? First, you can define it with fields. So what is the correlation between two fields in quantum gravity? Well, that's an interesting question, but here is a definition. So it's actually a non-local definition, but that is almost unavoidable if you want to preserve diffeomorphism invariance. So you perform your functional integral, and you take a field in point x, and then you average over all points y at a given geodesic distance from this point x. And this given geodesic distance, that depends, of course, on the metric. So you integrate over metrics. So this d of little g will be different from different little g's. But you do that, and then after that you average over all points x, because x should not have a special status. So this is actually a diffeomorphism invariant 2-point function, as you will do in ordinary field theory. And it's not so different from what you actually do on a lattice, in the sense that you would say, okay, let me measure the correlation between phi and y, x and y. Then I first use translation invariance on my lattice to make the average, to make absolute maximal use of the configuration I have generated on the lattice. And then if there's rotational symmetry, 4 pi or something like, pi over 4, then you also take the average over different orientations and so on. So you're really calculating this object here when you do Monte Carlo simulations. But never mind. Now let's take the situation where there's no field phi. So we simply drop the field phi here. We drop this functional integration. Then you get something like this. And this is the 2-point function I'm talking about. So it's diffeomorphism invariant, and it's between 2 points, x and y. So what's going on here? You take a point x, you will think average over all points, which has the distance r to this point, and then you average over all x. So this is basically the volume of a d-1 sphere, of radius are. And this is why it describes the fractional structure, because if the set of geometries has a fractional structure, then this will appear exactly in this way here. But now you can show, even in the continuum, you can show that this 2-point function, it falls off exponentially. And the factor there is, in fact, the average volume of spacetime. And on the lattice, it would say that in terms of lattice spacing, lattice links connecting 2 points, this 2-point function should fall off exactly like this, where this is the average. So here I have a cosmological constant, so the 4 volume, the d-dimensional volume is not fixed. This is valid in any dimension. The d-dimensional volume, this is not fixed, but it should fall off like this. So you can show that. And in 2D, you can calculate this analytically. And I've just tried to illustrate it here. So then n is the number of triangles, and then here's the distance between these 2 points. So if the distance is very large, clearly this geometry is going to look very different from this. So in a certain way, this R here, both here and here, it acts like a new coupling constant in the theory. And the probability distribution, you can calculate it analytically in the case of 2D. You'll find a function like this. So this is exactly the finite size scaling that we observe. And now, if you do not fix n, I mean the volume of space-time, but instead fix the cosmological constant and assume this critical value, I just put it to 0 for notational simplicity here, then the expectation value is inversely kind of proportional to the cosmological constant. This is just what this says here. And if you now include this in the action, then you have to sum over all of these to find the corresponding 2-point function. And this now falls off exponentially like this, where this is a half dimension of the ensemble. So this is exactly what we see. And this is exactly what we have used here. And I would say that I haven't really fully squeezed out the implication of this, but it could be very important also for not only for CDT, well, it is, as you saw, we have used it extensively, but also for DT, because then you are not really bound by trying to find a second order transition. So I will just stop here. Thank you very much for your patience. Okay.